John, you just tuned in. I'm not sure if you're rejoining the classroom, but just letting you know, I did update the class that we are going to have a quiz on Friday. There's going to be 2 questions in homework packet one on intermediate value theorem, one on continuity, and one on derivative sketching. So it's just going to be a 5-question exit ticket, and then it's going to count as a quiz grade. And then also for everyone who may have just joined class, homework packet 2 will be released today, and it's going to be slightly shorter, but it's going to be due before class next Monday. So I'm probably going to make the deadline at like 9 a.m. on Monday. Okay. Okay, so now everyone take 1 minute to get your notebook set up. Today we're going to be introduced to the limit definition of a derivative. I know we've tackled, I feel like, a few challenging topics recently, especially these past 2 days. And I think today will probably be also kind of challenging, but also it's one of these things that once we understand the concept of, we really don't need to use this that much more in calculus. So it's like we have to understand it conceptually, but for the rest of the year, if this is really difficult, don't worry too much, because I don't think it builds off of like our lesson today that much, but it is ultimately a core concept. So give another 20 seconds or so. Remember, just have your name, date, and then however you want to organize your notes. Okay, so first today we are going to take a look at the exit ticket from yesterday. So if you want to get out your work from that, I'm going to give 10 seconds for people to just like flip to that notebook sheet if you want to. And in the next 10 seconds, if you would like to volunteer like your answer or your thoughts, please chat your name. If not, I'm going to cold call on people just to get people's thought process and their answer. Tavera, you said you have a question. Go ahead.
On the exit ticket for that question, like it only gave us option 1 to pick from, like it didn't give us any.
Oh yeah, so the first 2 people who submitted the exit ticket, there were like maybe 6 or 7 people where it was like right after class. I messed up, so I didn't have the multiple choice options like enabled. So don't worry about that if you submitted like just option 1. But if you have like thoughts on it now, then yeah, just chat your name. But don't worry about that. Okay, so tackling question 1, the graph of f of x. So this is f of x, it's shown in the figure, and our task is to select the graph of the slopes of tangent lines from the graphs below. So between A, B, C, and D. Jamal, would you be able to come off mute and share like what your first step was when you tried to do the exit ticket?
Kind of confused. Kind of just, yes. So yeah.
Okay. Did you have like any place you thought you might want to start with, or you just purely guessed?
I kind of just guessed.
Okay. Okay. All right. Thanks for that. Marche, how about you?
So like the first thing I noticed was like it had the 0 point at 1. So
Gotcha.
I'm like it goes to the x-axis at 1. So I slimmed down to A or D, and then that's where I was kind of using the note sheet yesterday. So I think it was like if it increases, that's where like it flips, right? Or like like so it'd be A because the right side would be flipped, right? I don't know if it'd be A or
Gotcha.
D. But I'm not sure.
Yeah,
That's
so
the part.
your first part of thinking, the first part of your thinking is definitely right. So remember, my first tip is always to find the zero slopes. And that's exactly what you did. So on our graph, right, y equals f of x, we find there's 1, 0 slope right here, right? And we can find that by imagining the tangent lines. So the tangent line here is horizontal, right? So we know the slope is equal to 0. We can imagine that, like for here, for example, we know that the tangent line is clearly not equal to 0. So we know that it's a 0 slope here, and that corresponds to x equals 1, right? So when we look at our options A, B, C, and D, we need to find a graph that is at 0 at x equals 1. So we'll see for graph A at x equals 1, it's at 0, right? So that meets our first criteria. For B at x equals 1, well, it says the slope is positive. So that's obviously not right. So it's not going to be B. For C at x equals 1, it says our slope is negative. Well, that's also not right. And then at D, it says our slope is 1. So that meets our criteria. So it's either going to be A or D. Emily, do you want to come off of mute and share what you thought the answer was and why?
I said it was D because my thinking is if you look at the original graph, if it's decreasing in the original graph, we know that on the derivative is going to be below the x-axis.
Mm-hmm.
So from -1 to 1, it's decreasing, and then from 1 to infinity, from 2 to infinity, it's increasing to be above the x-axis. So I chose D.
Yep, that's exactly right. So D is our correct answer. So after we find the 0 slopes, right, we can look at the areas that aren't 0. So over here, right, this left half of the graph, we can see that the slope, let's just say, is negative. Remember, that's the part where we're looking for the signs of slopes. So cool. So we know that the slope here is negative. Well, we kind of can already tell the answer then, because if we look at part A, we look at the area that's to the left of 1, right? And we see that the slope here is positive, right? It's positive, so that's not right. And then we look at D, we see that the slope is negative. So D is our correct answer. And then if we want to confirm it, we can look at the other half of the graph. Like over here, the slope is going up, right? So we know it's positive. Slope is positive. And then we can see for part D to the right, the slope is also positive. Whereas for part A, the slope for answer A, the slope is negative. See that -1. So we know we're confirming that A is not right and B is correct. Okay. Thanks, Moshe and Emily, for participating. I'm going to skip this next question now, and we're going to move on to the main lesson of today, which is the limit definition of a derivative and understanding it graphically. So everyone who did the exit ticket today, I'm not going to go over the exit ticket specifically, but it was supposed to be a refresher for us to understand the concept of a secant line, right? So, or the average rate of change. So essentially, we're given a certain graph, right? And then a secant line connects 2 points. And then we're finding the average rate of change is the slope of this line that connects the 2 points. And then we do this to the equation f of b minus f of a, right, over b minus a. So let's say this is the graph. B is here, A is here, f of b is the actual point, f of a is like the actual point. So then we subtract again, if you recall, it's just the change in y over change in x. Like we're just calculating for the slope. So this is what this is calculating for. So the slope is equal to f of b minus f of a. Now, this is the average rate of change. average rate of change, so AROC. When we look at derivatives, and we're looking at the limit definition of a derivative today, derivatives tell us always the instantaneous rate of change. So that's different. Like secant lines, this isn't very, like, it's not very like accurate, right? If we're looking at like what's the average rate of change, it connects two dots that are like really far away from each other, 2 points that are really far away from each other, and then asks us about the slope. It's like, that's math, I guess, but it's not really useful. Like it doesn't show us all this information in between. Whereas if we find the instantaneous rates of change, which is what derivatives tell us, it tells us the exact slope at a certain point. So like at f of a, it can tell us the exact slope. So we're going to try to apply our knowledge of secant lines to derivatives. So we're going to move from average rate of change to instantaneous rate of change. And that is what the limit definition of a derivative allows us to do. You don't really have to include this part in your notes. It's just me drawing, but I'll give 5 seconds just if anyone wants to copy it down. You can go ahead. So today we're moving from what we did in the do now, from the secant lines and average rate of change, and we're going to see how we can use limits to turn that into instantaneous rate of change. Yeah, Taver, are you asking me to scroll back up to the exit ticket or just right here? I'm going to leave this here for another 10 seconds. Okay. Okay, so this is kind of an example of showing us how we can use secant lines to kind of secant lines and the average rate of change to get the instantaneous rate of change. So what this says here is that each graph includes the same function. F of x is equal to this function, right? So each of these graphs below, like graphs 1, 2, 3, and 4, this red line, that is the function. So it's the exact same in every one of the graphs. So in 1, 2, 3, and 4, this red line is the exact same. Next, we're told that each graph includes the same tangent line to the curve at x equals 1. So that is this blue line. So you'll see that this blue line provides a tangent line to the curve, right? Because the curve is the red line, right? The blue line provides a tangent line to the curve in every single one of these graphs. So it's the exact same blue line in each one of these graphs. Now, the thing is, each graph contains a different secant line to the curve on various intervals. So the green line is where this differs. Actually, just to preface, I'm also not going to ask you to draw all these graphs because I understand that's a lot to draw. But I will ask you to kind of like take notes on your thought process as you're going through this. So if you like have any realizations or like understandings, just to jot those down so you're like keeping engaged with the material. So just to reiterate, the red lines, the function is the exact same. The blue line is the tangent line. Those are the exact same. But what's different is the secant line, so the average rate of change. So you'll notice in graph 1, the secant line connects these 2 points, right? So they're kind of far away. In graph 2, it connects these 2 points, so they're closer, right? It connects, in here it connects x equals 1 and x equals 4. In this graph, it connects x equals 1 and x equals 3. So the secant line, the points become closer, right? In graph 3, well, now we're getting really close. The secant line is connecting 1 and 2, right? And then in this one, it's even closer. It's connecting 1 and 1.5. X equals 1 and 1.5. And the points are very close together now. So I'm going to give everyone 30 seconds to think about this question. What do you notice about the secant lines as the intervals get smaller? So here's like the largest interval, right? and here's the smallest interval. So what do you guys notice as the intervals become smaller about this green line, about the secant line? I'm going to give 30 seconds or so, and then if you have a thought, if you have just, what are your thoughts? I will call on people, or you can send a chat. Okay. Thanks, Clarissa. Thanks, Naima. So I want people to pay attention close to the secant line, to the green line, and see how it changes, right? And as the interval gets smaller, like what happens to the secant line? All right, thanks, Kalia. So yeah, I am seeing a lot of people say the answer is that the secant line does get less steep, and that is absolutely correct. You'll notice in this first graph, it's pointing upwards more, and then in this last graph, right, it's like not pointing upwards as much. However, that's not the complete answer that I'm looking for. I would like people to think about, like, compared to the other lines on the graph, right? Where's the secant line? Like, how is it changing if we want to compare it to the other lines in the graph? I'll give another 30 seconds. Okay, yeah, we're getting more. Thanks, Ruchal. Thanks, Naima. That's exactly right. So you guys are definitely on the right track. Okay, I'm gonna cold call. I'm gonna start with Mubarak, then Naima. Mubarak, could you come off of mute and give your thoughts on what you noticed about the secant line?
For graph 4?
Sorry, go ahead.
Which one? For which one?
So we are looking at basically all the graphs and how it changes, how the secant line changes. So how does the green line change between these 4 graphs?
I guess over time it's decreasing.
Gotcha, yeah, so that is one element. It's becoming less steep. But is there anything else you notice? How about how it compares to the tangent line? The tangent line is the blue line.
It's always greater than the tangent line.
Okay. Okay, awesome, thanks. I'm gonna move on now to Naima. Do you wanna come off of mute and talk about what you noticed?
I said that the secant line is getting less steep and that is getting closer to the blue line. That's the tangent line, right?
Yes, exactly. So yeah, that's the key observation we're trying to make here. So basically, as the intervals get smaller, the secant line begins to look like the tangent line. So that's an interesting observation, right? When we first looked at, let's say, a secant line for, like when I demonstrated this earlier, right? A secant line for this type of graph, I connected these 2 dots, right? that's like not a very good representation of of like an instantaneous rate of change, right? Because they're so far apart, it's clearly just like cuts across the graph, and it doesn't represent the slope of the graph very, very well. But the point here is, what if I make the dots, the secant line, what if I make it really close together? Well, if I get really close together and I connect this secant line, right? Or I won't even, those are almost too close. Let's say like this dot and this dot, right? And I connect this secant line. Well, now it's starting to look kind of like the instantaneous rate of change. It's starting to look like a tangent line. It's starting to look like it'd be a better representation of the slope, right? So that's the key takeaway we're looking at here. When we take a secant line and then we move the points really close together, it starts to become the tangent line. So I would really like everyone to internalize that idea here and write this down. As the intervals get smaller, the secant begins to resemble the tangent line. And more important than that is just like understanding this concept. I'm going to go over it again really quick. So we have, let's say, a function, right? A parabola. We have a parabola, right? And then we start off with a secant line, which is the average rate of change, right? And it's probably not a very good representation of the average rate of change, of like the rate of change of anything, right? It basically cuts through the graph. Like technically it is the average rate of change, but it's not a very good representation of the slope of the graph at all, like it at any point, right? Like again, let's say the tangent line here, it is a much better representation, right? Because the tangent line, well, the tangent line is the exact representation of the slope at any point. So that's the tangent line's really like what calculus is all about. That's what we want to deal with. However, we'll notice that when we make the secant line and we move the points closer together, so let's say I move the points instead of that far away to over here, and now I draw a secant line, I'm going to notice that it's starting to really look like a tangent line. It's starting to be a pretty good representation of the slope at this point, right? This secant line seems like it's a pretty good representation of the slope of the graph at like this point, this area. Okay, I'm going to give everyone 10 more seconds. Okay, so now I'm just going to kind of start writing, but so this is where we get to our core idea with today, which is the limit definition of slope of a tangent line. But really what that means is the limit definition of a derivative. All right, thanks for letting me know, Alicia. So yeah, so now we're looking at the limit definition of the slope of a tangent line, which is really the derivative. So let's say we have a function, right? And we have this tangent line, or this, yeah. So what we showed earlier was that as the interval gets smaller and smaller, okay, I'm gonna give everyone like 10 to 15 seconds just to catch up. Okay, I'm gonna call on someone just really quick for a check for understanding. So as the interval gets smaller and smaller, the secant line begins to look like blank. Shanice, would you be able to come off of mute and tell me, as the interval gets smaller and smaller, what does the secant line begin to resemble? What does it begin to look like?
It begins to resemble the tangent line.
Yep, that's exactly right. Thank you. It begins to look like the tangent line. This also means that this should be pretty intuitive, but the slope of the secant line begins to approach, I guess. It begins to look like, yeah, the slope begins to look like the slope of the tangent line. So then we're kind of faced with this idea, like, what if I made, right, as I get these 2 points together, right, so let's say the secant line, the 2 points are really close, right? Well, what if I made them infinitely close together? Like, so that they're like getting infinitely smaller and smaller. Like, isn't it almost essentially a tangent line then? It's like the points are so close together, again, it's like infinitely close together. So that's why we're using limits, basically. Just to express that idea, we originally have this, the slope of the tangent line is f of b minus f of a over b minus a, right? Well, let's say this is at, let's say x equals 1, right? This point is at x equals 1. Well, if I really want to find the exact slope at this point, right, at this one point, shouldn't I just do like f of 1 minus f of 1 over 1 minus 1, right? Because then there's no difference in the points. Like originally, like, let's say I wanted to estimate it, I could do like f of 3 minus f of 1, or f of like 0, let's say, over 3 minus 0. But we already know, like, these secant lines, they're not a very good estimate, right? Because these points are really far apart, right? If we want to get a really good estimate, we should just do, like, use those exact points, f1 minus f of 1 over 1 minus 1. But of course, that's equal to 0 over 0, so it's undefined. So we can't do this exactly. Right? So it's undefined. So it's kind of like, what do we do? I'm going to give everyone 15 seconds to catch up. So just to be clear, this is the slope of the secant line equation. Yeah, that's exactly right. So you keep on making the values smaller, right? So that's why we're going to use limits. So we use limits. So using the same example, like f of 1 minus f of 1 over 1 minus 1, let's say we did instead f of x minus f of 1 over x minus 1, but we did it so it's at the limit as x approaches 1. So now we're doing something where the x, right, in f of x and in the denominator, it's approaching 1, so it's getting really close to 1, because that's what limits that's what limits are, right? Limits are essentially like, they're telling us a value as like the function approaches a certain x value, right? So here's where we're like, our goal of making an infinitely small interval for a secant line, we kind of achieve that because we're using limits now. So essentially what this is saying is, as x approaches 1, the slope equation approaches the slope of the tangent line. As x approaches 1, the slope equation approaches the slope of the tangent line. That's what this limit is telling us, right? Because we're constantly, limits, like, the whole idea is, it's like, well, what is this value approaching? We're getting infinitely close to this value, right? So as we get closer and closer to 1, we get a secant line that's basically so close to a tangent line, right? It's infinitely close to a tangent line that it basically becomes a tangent line. So now this is this is what we call the alternative definition of a limit. So we kind of achieved like our first definition. So there's actually two definitions for a limit, but our first big one we already solved. So how that is written out is the limit as the limit of x approaches a, f of x minus f of a over x minus a. So it's the same exact like format that we used here. Same exact idea. We're just substituting instead of 1 now, we're substituting in like a general number like a. So now if I want to find the limit at x equals 3 or something, well, now I'm basically using this exact format with like a secant line slope, right? And then getting infinitely close to 3. And then that's going to tell us basically the slope of the tangent line. So I'm going to give everyone 10 seconds to copy this down. And again, this is called the alternative definition of a limit. So Naima, yeah, you had a great question. So Naima suggested that if x was 3, then a would be like 2.99 or something like that. Yeah, I mean, that's a really good way to think about it. It would be really close to 3, but the idea with these limits, right, is that it's not even like 2.99 or 2.99999. It's like infinitely close to 3. So like the 2.9s like stretch on forever to the point where it's so close, it basically becomes the tangent line. So that's what, yeah. So this definition of the limit gives us the slope of the tangent line, which again is just the definition of a derivative. Now, for the last 6 minutes of class, I am going to talk about really quickly, there is the alternative definition of a limit, and this is a completely valid definition. Okay, totally valid. You will probably use it at some point on the AP test. There is also a second definition, which is identical to the first one. It's just represented in a different way. But I think this definition, so we'll just call this the definition of a limit. I think this one's more confusing, to be honest. So don't panic if you like don't understand this definition right now. We're probably going to go over this more tomorrow. Like this one, I feel like makes sense, right? Because it looks so similar to the secant line equation that we were dealing with, right? Like f of b minus f of a over b minus a. It looks extremely similar to that, right? This definition of the limit, I'm going to write it out. It's the limit as h approaches 0 for f of a plus h minus f of a over h. So it's actually just the exact same idea. So our concept, our understanding of secant lines and like the infinitely close idea, it hasn't changed. But this is just represented differently. So I'm going to give everyone 10 seconds or so to write that down. And I mean, these are ultimately like, this is basically the whole lesson, understanding these two equations. So this is, we're going to probably spend tomorrow also applying this definition. But yeah, this is the entire lesson. So I think this second definition, again, is more confusing, but the idea is the same. So you notice that it's f of a plus h, right? minus f of a in the numerator, but it says h approaches 0. So as h approaches 0, that also means the difference between f of a and f of a plus h and f of a becomes infinitely small, right? Right? As f of a plus h, this becomes like close to 0. So it's like 0.0001, let's say, right? So what is f of a plus 0.001 minus f of a? It's basically going to be 2 points that are extremely close together. Also in the numerator, h is approaching 0. So it's approaching, it's like 0.001. So it's the exact same idea, right? Because if we look for the alternative definition, right, over here, if x is approaching a, right, then what is x minus a going to be? It's also going to be really close to 0 because x is approaching a, right? So x is very close to a, and then we're subtracting a. So it's going to be very close to 0. It's going to be like 0.0001 or whatever. And then the top is the same. F of x minus f of a. Well, x is approaching a, so it's going to be almost like f of a minus f of a, right? So it's also going to be close to 0.00 whatever. The whole idea is that the numerator and the denominator, they're getting infinitely close. And so it's actually the exact same idea for the definition of a limit, just represented differently. Okay, so I think that's enough for today. Take time to try to really understand conceptually the definitions of the limit for the alternative and the second one. They're both equally valid. Besides that, just remember to turn in your notes, exit ticket, etc. The homework packet 2 will be coming out tonight. Again, if you have not done homework packet 1, I highly suggest you get that done as soon as possible so work doesn't pile up. And if you have continuing concerns with that, please email me because I know there are some students who still have not turned that in. And then the final update is that on Friday, our exit ticket is going to be a quiz. But yeah, that's it. So thank you all for coming today, and I'm going to see you all tomorrow. Bye, everyone.
Mr. Wang,
Yeah, what's up?